Hey Ramblers, this video covers the material in chapter 12.5 in our textbook and deals with the volumes of cones and pyramids. Now, in an earlier section, we learned how to find the surface area of cones and pyramids, and we saw that their formulas were really closely related. Well, the same thing with volumes. We'll find that if we can understand the formula for the volume of a pyramid, the volume of a cone is very, very similar to that. We're also going to look at the relationship between the cross-section of a pyramid and a cone and its base, and we'll learn how to solve problems relating to that. All right, Ramblers, I hope this video helps. Thanks for watching. Just as prisms and cylinders are closely related for their formulas for surface area and volume, pyramids and cones are closely related as well. Let's start off looking at pyramids first, and we'll introduce the formula for the volume of a pyramid. You recall from the previous video the different parts of a pyramid: the vertex, the lateral edge, the base edge, and the base. But we also want to look at not the slant height, which is what is used to find the area or the surface area of a pyramid. What's important with volume is that we look at the altitude. And the altitude stretches from the vertex down to the center of the base. And that's typically in a square-based pyramid where the diagonals intersect. So you'll recall that we had several different helpful triangles that I called them. You had the triangle involving the slant height and the altitude. We also had the edge, the lateral edge, and the altitude. We had a slant height and the edge triangle kind of on the face. And of course on the base you'd have the half of a diagonal and the apothem. These were all triangles we'd use to find the different measures of the dimensions we'd need. Well, for volume, it's going to be simply the altitude is the most important part when finding the volume. And the formula for volume of a pyramid is 1/3 the area of the base times the altitude. Now you may recognize that the second part of this, the area of the base times the altitude, is simply finding the volume of a prism. So in a way you can think of a pyramid as having 1/3 the volume of a prism with the same base and the same height. Okay, now don't get this confused with surface area. Surface area is 1/2 perimeter of the base times the slant height. Volume is 1/3 area of the base times the altitude. Now, let's take a look at, see whether this applies to cones. Okay, with cones, there aren't as many parts. Well, we have a vertex and a lateral edge, a base and a base edge, but there is no slant height. The slant height is the same as a lateral edge. The cone's altitude, of course, runs from the vertex through the center of the cone to the center of the circular base. To find the cone's volume, we're simply going to take 1/3 the area of the base times the altitude. And since the base is always a circle, that formula for the volume of a cone is 1/3 pi r squared times h. And once again, h is the altitude from the vertex to the center of the base. Now there really aren't as many triangles that are helpful in a cone because of the circular base, but there is one that we'll use frequently, and that is the triangle made up of the altitude, the lateral edge, or the slant height, same thing, and the radius of the base. Okay, so please get this formula for the volume of a cone and the volume of a pyramid in your notes. Put them together on that same page with all your other surface area and volume formulas. And then let's take a look at one last theorem as it relates to cones and pyramids involving the cross section. So let's talk about that next. You'll recall that a cross section is the intersection of a plane and a solid like a pyramid. And this cross section if it is done parallel to the base, the cross-section will be similar to the base. So, given that condition, that the cross-section is similar to the base, we have an interesting theorem, and it reads as such. In a pyramid or cone, the ratio of the area of a cross-section to the area of the base equals the square of the ratio of the figure's respective distance from the vertex. Now, what does that mean? Well, it means this. If you look at the area of the cross-section, that's the blue area, and divide it by the area of the base, that would equal PU, kind of the distance of the cross-section to the vertex, over PQ, which is the entire altitude of the pyramid. So you'll notice that this ratio, the ratio of the area of the cross-section to area of the base, equals PU over PQ squared. So as I manipulate the cross-section and make it higher or lower, you can see that the two proportions, that the ratios always stay same, which means to say that they're proportional. So the area of the cross-section to the area of the base is equal to their respective distances from the vertex squared. It's pretty complicated. Okay, let's take a look at what a cross-section of a cone would look like. Now, as we look at a cone and its cross-sections, we can see that the same relationship is true. If we look at the area of a cross-section over the area of a base, that will equal the distance of the cross-section to the vertex over the altitude squared. And no matter how we would manipulate this, the area of the green circle to the area of the blue circle will equal the ratio of the distances to the vertex squared. Okay, Ramblers, let's take a look at a problem before we wrap things up. Thanks for watching. Number 14 on page 587 is a problem which is going to end up being showing us how to find the volume of a frustum. But for now, we start out with the entire cone. And in part A, they ask for the what is x. Well, we're just going to use some of the similar triangle techniques we learned in chapter 8 to set up a proportion, where we know that by the side splitter, x over 10 equals 12 over 8. Now be careful. If we had known the radii, we could not have set up this side splitter proportion. Be careful that you don't set up a side splitter when what you should be using is similar triangles. Alright, if I solve for x, I see that x equals 15. So then in part B, they'd like to know what the radii of the circles are. Well, that's going to break down into two right triangles. If I know that in the top triangle I have a 12, 15, then the upper radius must be 9. And then in the larger cone, if my hypotenuse is 25 and my height is 20, then the third side has to be 15. So my two radii are 9 and 15. Okay, then in part C, they ask us to find the volume of the smaller cone. Well, volume, as you know, is going to equal 1/3 the area of the base times the altitude. So not times the slant height, that's surface area. So we're going to multiply times the altitude, which is 12. So I'll get 1/3 area of the base is going to end up being 9 squared pi times that altitude of 12. And that will equal 324 pi. To find the volume of the larger cone, we're going to do the same thing. But this will be 1/3 15 squared pi times the altitude of 20, which equals 1500 pi. Okay, for part E, they want to find the volume of the frustum. Well, that's simply going to be subtracting the volume of the top cone from the larger volume of the bottom cone. So we're going to get 1500 pi minus 324 pi, which will equal 1176 pi. Okay, let's take a look at one more problem let's look at a pyramid number 19 on page 588. Okay, number 19 on page 588, they ask us to find the volume of the pyramid. So volume, of course, equals 1/3 the area of the base times the height, and then height being the altitude of the pyramid, not the slant height. So our trick is to first find the area of the base, and the area of the base looks like an isosceles triangle whose has a base of 6 and two legs of 5. So I'm going to drop an altitude from the vertex to the base, and since it's an isosceles triangle, that will bisect the base into two parts of 3 each. And now it looks like we have a 3, 4, 5 triangle. So the height of the triangular base is 4. So to find the area of the triangular base, it's just going to be 1/2 the isosceles triangle's base, 6, times the isosceles triangle's height of 4. So that's the area of my base. Now I'm just going to multiply it times the height. To do that, I need to look at another triangle. This one is going to be a right triangle, which has a leg of 5, a height we don't know, and a hypotenuse of 13. Well, once again, by triples, we know that the height must equal 12. So now I have all the components for my volume formula, and I just have to multiply it out. And when I multiply it all out, I get 48. Okay, good luck, Ramblers.